Yeah, thank you. So my name is Adeni. I'm with the Skoltech Machines 2.0 team. And you might be wondering why 2.0? So that's because we've kind of have been on Mars before. This is the MDRS station. And we sort of envisioned this mission as saving our former crew commander, Divya Shankar. But anyways, so today we'll be taking you through our concept about a possible manned mission to Mars. This is a team. This is the four of us who are here. This is Divya, hopefully, that we'll be able to save by doing a Mars mission. First of all, we'll look at the mission roadmap. So we think of this as a 600-day mission, a two-person crew mission with about 45 tons of payload. Now, what are the ingredients of a successful mission? We think about it as having a successful launch, basically, having successful flybys, which is the aim of the mission, and a successful re-entry. And if hopefully we land successfully, we could say that the mission is accomplished. As a bonus, we possibly might be able to fly by Venus as well. So we'll look at the different components of the mission, and we'll talk about each one of them more in detail. So I'll hand over now to Alexander to talk about the launch opportunities.
Thank you. According to the competition rules, we need to send our mission to the Mars flyby till 2024. Unfortunately, we cannot perform free return flyby in these dates. That's why our trajectory will look like the following. It will consist of 3 legs. The first one starts with Earth launch. Earth launch goes to the Venus flyby, then goes to the Mars and Mars flyby, and then goes to Earth, descending and landing. The total duration of the whole mission is 582 days, and to perform such a mission, we will need 12.22 kilometers per second total delta V. And we can reach such a high delta V with SLS and Orion spacecrafts. However, it also means that we will have high re-entry velocities. That's why we will need to, arrival velocity will be 12.85 kilometers per second. That's why we will need to use the skip re-entry maneuver, which consists of Earth approaching, dive into atmosphere to decelerate and reduce kinetic energy, then the skip trajectory to reduce the heat by radiation, and traditional re-entry with landing by parachutes in waters of Atlantic Ocean. The best parameters of our descending trajectory will be reached with 7 degrees angle of attack and entry angle of 2 degrees. It leads to higher down ranges. It's here, the red line. However, our angles of attack, our horizontal angles, velocity and altitude will change smoothly. That's why our G loads will be very low, up to 1.5 G along to each axis. To perform all the gravitational maneuver and re-entry strategy, we will need to use a DCS system, which consists of sun sensor, star tracker, IMU, GPS, and CCD detector, and 12 hydrazine monopropellant thrusters. Our communication system consists of 2 channels. The first one is RF Ka-band 32 GHz channel and laser link channel. We'll use RF to provide telemetry and telecommand data, and laser link to provide HD video and payload data. Our primary goal in designing communication system is to use existing infrastructure, which consists on-ground deep space network and geo satellites like Inmarsat 6. Now let's turn to the spacecraft design, and Veronica will tell you everything about it.
This is our Gemini Mars spacecraft. It consists of a habitat and laboratory module, 2 beam modules provided by Bigelow Aerospace Company, and Orion spacecraft. First of all, why did we choose Orion? Because it's already designed for long-term missions and for return from interplanetary trajectory. And also the most powerful rocket, SLS, is designed to carry Orion spacecraft. And development goes according to the schedule. And the first manned flight announced in 12/21. So we believe that among any other options we could choose, Orion spacecraft really have a chance to be ready by 12/21. Habitat and laboratory module is ISS Node 2 derived module. We chose one of ISS module because we can take a lot of systems from ISS without development, and they already will be included in cost of this module. It's not too big and it's not too small. But we need to make several changes. First of all, we need to put centrifuge inside, so we need a system to accommodate it. We need a system to attach additional racks, which will be installed inside beam modules after launch. We also need to change one common berthing mechanism hatch to NASA docking system hatch to dock with Orion. And we need to install inflatable airlock just in case of emergency situation to perform EVA. 2 crew quarters are inside HLM, so like Node 2 has 2 crew quarters. And also we have international standard payload racks which accommodate advanced life support system. And beam modules provide additional space for galley, for storage, for experimental racks and science racks, but these racks should be just a little bit modified for beam module dimensions. We limited weight of one rack by 600 kilograms, and we got the total weight of our spacecraft 45 tons and living volume 101 cubic meters. It's important because there is a psychological standard that every astronaut should have 50 cubic meters of living space. And also you can see the launch configuration of our spacecraft. The Orion spacecraft on the top under the escape launch system because of safety concerns. So transportation and docking maneuvers should be performed like this. And now let's talk about radiation. We actually made the calculations in Giant4. This is a software developed in CERN for calculations of radiation. We actually use a simple module, but we hope that it can be relevant. These are standards of exposure dose for LEO carrier set by International Commission on Radiological Protection. So we try to find the thickness of materials which provide a dose lower than these numbers. And we found that 8 to 9 millimeters of polyethylene can protect our astronauts with dose about 0.7 and also you can see 6 or 7 millimeters of aluminum. So in that case we can launch to Mars 35 years old male astronauts or 45 years old female astronaut. And now I'll pass to Natalia.
Okay, so to keep our astronauts alive, we have to have a life support system on board, as well as think through the countermeasures and the food supply. So let's look into the simplified version of the Advanced Life Support System. So as you know that during long-term space missions, the amount of consumables such as oxygen and water is very limited. And therefore, we would need to have, the resupply is not an option in that case. And this is when we need to think about the atmosphere recycling processes. And this is where air utilization system comes into play. So what happens? The carbon dioxide is removed from the cabin air through the carbon dioxide removal assembly, and then it is reacted with the hydrogen inside the Sabatier reactor. The product of this reaction would be methane that is potentially could be used as additional fuel source, and also water that is stored in special tanks. The wastewater, water from the wastewater tank is then reused in the air production process, and clean water from the clean water tank goes through the delivery system back into the crew cabin. Also, the biological waste part of it can be also reused and goes through the urine waste recovery system, and then goes back through the quality control into the crew cabin. Also, since we'll have the nitrogen and oxygen leakages, we'll have to install additional tanks to eliminate these leakages. And also, we're thinking that it could be feasible to use nitrogen, to produce nitrogen from the waste tank that has inside ammonium or hydrogen. So for the food supply, surely, as a lot of teams mentioned today, we think about using the green hub like for this. And the other idea that I thought was very interesting, and this actually was the solution proposed for NASA Open Challenge. This is the 3D printing for food supplies. The basic idea behind it, let's say, so it removes all the components that may spoil the food, and the remaining part is powdered and then combined into the small packages. And then during the mission, for example, you can use those nutrition component. It goes through one extruder and another one adds the flavor to that food. This is a new concept we thought may be interesting, but as later we'll see that there are alternatives for that if this one does not work, since it has a pretty low TRL level. As for countermeasures, along with the traditional pharmacological treatment, we'd propose to install the short radius centrifuge. There are a lot of different advantages, actually, of that system compared to traditional training equipment. First of all, it helps to mitigate VIP problem, which is the problem of increase of intracranial pressure. And to make the centrifugation more efficient, we plan to also pair it with the active exercise, such as ergometer and steppers. By doing this, we would also save some time that usually crew spends for the traditional training. And while it's not operational, like this centrifuge, it also can be used as a research platform therefore also increasing the scientific utility for the mission.
Right, so I said at the beginning that the mission is sort of to save our former commander, but actually we also feel like you have to give the mission a mission if you want it to be successful. So basically, what would the crew be doing over this 600-day period? So we divided this into 3 themes: human research, plant research, and technology development. So for human research, we'll be looking at behavioral health, the effect of microgravity on human physiology over extended space journeys, which sort of extends what is being done currently on the ISS. Also, we'll study the effect of microgravity on plant growth over long duration. For technology development, lots of opportunities for ambient air analysis, for acoustics and diagnosis of spectral levels as you travel along to design missions with noise reduction. They also have lots of opportunities for astronomy or for sending CubeSats into Readiness, for example, during the flybys. So I've been talking about most of the subsystems these subsystems have to be powered. So here we have this main power subsystem requirements. So here we're using the kind of thinking behind this was basically you have three main parts of any power subsystem is generation, distribution, and storage. So our requirement for each of these sub-themes was that the power system should be able to supply a continuous source of electrical power to all subsystem loads during the entire mission life. For distribution, the power subsystem should be able to manage, regulate, and distribute electrical power. And for storage, the power subsystem shall be able to store and generate the power for peak power demand and during eclipse period. So for this, we know that the entire load for our spacecraft is about 20 kilowatts. So we decided that we'll be using what's already on the Orion. So 4 Orion solar panels with cumulative 11.4 kilowatts power rating, 2 UltraFlex panels, 2 for redundancy, that give cumulative about 19 kilowatts. For storage and distribution, we'll be using 3 rechargeable lithium-ion batteries. For distribution, 28-volt DC power buses, and a 4th battery is installed for redundancy that can generate, that can supply about 500 watts of 28 VDC for a period of about 12 hours. So for distribution, we use the Orion power distribution system. All right, so as per technology readiness level, one of the key ideas towards developing this mission was that most of the stuff and the component that we'll be using should already have a very high level of technology readiness. So as already been mentioned, so Orion, for example, is on track to be developed and to be launched in 2018, 2019, somewhere there. So most of the other systems also have already advanced levels of technology readiness. The only one that here you see is the 3D footprinter, which could easily be replaced with something else. So as per risk analysis, so there are lots of different risks that's associated with missions like this. You would need a different presentation to go through all the risks, but we decided to focus mainly, so basically you have technical and non-technical risks. We decided to focus on the ones that we feel might actually be very critical to the mission actually going on at all. So first of all, we feel like schedule failure is the biggest one. So if the subsystems, for example, like Orion or the SLS do not launch according to plan, then we might likely miss the window of opportunity that we have as per timeline for launch. So we also feel like lack of support from the government is a big risk. Lack of funding and cost overrun could also be some of the factors that might affect. As for technical risks, we have backup slides if you're interested in that. So for cost estimation, here is a very brief overview of what the costs look like for launch and spacecraft structure, and for the mission subsystems, mission operations cost, and miscellaneous cost. We have a total cost of about $3 billion, so we added a window of about 15 to 20% for inflation and also for cost overruns to get a final of about $3.5 billion for the final cost. So this is the schedule for the implementation of our Gemini Mars mission. So here you see concept studies, and this year, concept and technology development towards the middle of July, the middle of 2017. Now here you see some of the critical areas that might affect the implementation of the plan. So for example, here in 2018, that's when SLS and Orion launches is supposed to be conducted. So if that is conducted, this timeline would remain and be valid, and we expect to launch on the 18th of November, 2021. So what are the conclusions we could make from this? We've demonstrated by leveraging existing technology and combining SLS and Orion, it is indeed possible to launch a manned mission by 2024. We've demonstrated that technology readiness level of components employed in these designs are very high, meaning tech risks are minimized. And we've demonstrated that cost associated with this design demonstrates the feasibility of a manned Mars mission. And hopefully, it's Mars or bust. So thank you very much. Okay. Very happy to take your questions.
You showed a 45-ton spacecraft. Does that include some propellant, or is that all the inert spacecraft? Because, and then what is your delta V leaving LEO for Venus? Because I'm concerned that there might not be the mass budget for this.
Actually, 45 tons is the mass of the whole spacecraft, including the propellant, including all the facilities inside. And yeah, we have mass. Okay. And about Delta V, actually, we decided to make the direct launch. And however, in case we will try to perform the same trajectory with LEO, we will need like 4 Delta V kilometers, Delta V approximately 4 kilometers per second. However, we will not use our LEO, we will not launch to the LEO in our mission.
So you're lighting the upper stage suborbital like a Saturn V, and then is that what you're doing? Is that?
Yes, actually, we will do like a Saturn V, just the direct launch to the Venus without orbiting.
I understand. Okay, thank you. Other questions from the panel?
My favorite question about, you know, as you fly by Venus, have you done all the calculations on the, because it gets pretty hot?
Yes, and actually, our flyby will be at altitude like 11,000 kilometers.
But I mean, it's also solar,
Huh?
the solar radiation.
Oh. Can you repeat the?
Well, one of the things, I was involved a little bit in Dennis Tito's analysis, and it's really hard when you start looking at you're getting a lot more solar radiation because you're at Venus's distance from the sun. So has that been calculated in here?
I think in question of radiation, we expected the most dangerous situation when we have solar flare.
Yeah, well, there's both solar flares and the thermal load that you get on the spacecraft. So there's two things. One is the solar radiation from a flare, because you're at, Venus's distance from the sun, so it's the square of the distance. And the second is just the energy flux on the spacecraft. You design a spacecraft that operates in Earth orbit. I mean, these things have been designed for that, but they have a thermal, rejection system and so forth. So my question is, have you done the calculations that what additional systems you need on board the spacecraft as it spends the several months that close to the sun?
Okay, for radiation, I can say that there are standard modules of fluxes.
Okay.
And we just took the standard modules. For thermal, we expect thermal system like ISS thermal system, maybe with slightly modifications for this flight.
Any further questions? All right, thank you very much.